Hello, everybody. My name is Bill Hanson. I'm the Director of Competition Operations for the Spaceport America Cup, and I will want to welcome all of you to the 2023 judging team and to our Rocketry 501 training. As a disclaimer, I would have liked to have done this interactively via Zoom. However, I'm currently up in the north woods of Minnesota on an extremely tenuous internet connection, and so I figure I better just record this, get it out, and then we can have a interactive session with questions and answers later on after once I get back into the land of good internet connections. So with that in mind, let's get started. Okay, so welcome to everybody. I really very much appreciate your willingness to pitch in and be part of this competition. You're going to make a huge difference for the young folks on the teams, and I think that's really what it's all about. This is what keeps me coming back year after year, are the student teams. And so what we're going to cover today is we're going to basically jump from the Rocketry 101 presentation, which if you're new to Rocketry, you haven't looked at that, you ought to take a look at that. But we're going to cover the difference between the basic hobby rockets that we talked about in Rocketry 101 and the Spaceport America Cup rockets. And we're going to talk about the scoring procedures in some depth to give you a better handle on how we're thinking about the scoring rubrics. Okay, so the key differences, or as shown, we're talking about dual deployment for the recovery, a lot lot different electronics that you'll see at the cup. You'll see things like active trajectory control, transonic and supersonic flight. The teams have to worry about things like vibration and electromagnetic interference. For the 30,000 foot teams, high altitude challenge presents its own challenges. Normally, we would have some teams with liquid motors, but I'm not going to talk about that because our last liquid team dropped out about 3 days ago. So we don't have any liquid motors and the payload. So back to the Rocketry 101, the basic hobby rocket. You got your nose cone, airframes, fins, motor, and a parachute. And that was pretty much it. So those are fairly basic beasts. But when we get to a cup rocket, now we've got more moving parts. Obviously, starting still got the nose cone, but now we have a payload, and so the teams have to carry that 8.8 pound payload to altitude. The regular airframe, they have now avionics, so both altimeters to control their parachute injection. Plus, they're going to have GPS and some will have telemetry. And then you're going to have, instead of one parachute, you're going to have two main parachutes. Or you're going to have a drogue parachute and a main parachute. And so we'll explain why that is here in our next slide. So a pretty typical hobby rocket flight. The motor accelerates, you exit the top of the launch rail, and the rocket is flying at that point, but it's still accelerating because the motor has not burned out. Once it reaches the motor burnout and maximum velocity, then it goes to the top of its trajectory, and then at the apogee, the parachute will deploy, and the rocket will land somewhere downrange. Which is good if you're only launching to 1,000 feet or so, but now we're launching to 10,000 feet and 30,000 feet, and if we put out a parachute at 30,000 feet and then let the rocket drift in the high New Mexico winds, that thing is going to be miles away. And so the way we solve this is by dual deployment. And as before, you have the ignition, the rocket's going up, motor burns out. And at apogee, we have a parachute deployment, but instead this is a small deployment, small chute that basically gets the rockets falling essentially straight down at a controlled rate of speed, which is usually somewhere around 90 feet per second. And then down at 1,500 feet, then the main chute deploys and then the rocket lands. And so, because we get the rocket falling in a controlled manner, get toward the ground pretty fast, and it doesn't have enough time to drift. and because of that, then the rocket uh, doesn't go nearly as far. That's not to say that things don't happen. We do occasionally have the main deployed apogee, and of course, the New Mexico winds can create a challenge. So it's still not unknown for the rockets to come down several miles away from the launch point. But the dual deployment setup certainly helps this out. But because of the dual deployment, then you have to have a more complex set of electronics. And so what you normally have is you have two different altimeters that each have two different channels, one to fire the main chute and one to fire the drogue chute. And these things back themselves up. And so normally we use black powder charges to separate the rocket from separate the airframe either from the on the drogue chute side on the left side. That charge will fire once it gets to altitude, and then right behind it, then you're going to have a backup. The other altimeter is going to fire the backup charge after a second or two, or maybe 100 feet altitude delay, and so you've got dual redundant systems to make sure that the drogue gets out when it's supposed to, and then at 1,500 feet, then the main chute side of the altimeter fires its black powder wells to separate the rocket at that point and to get the main chute out. So this is a commercial kind of pre-printed avionics bay. You'll see lots and lots of different variations of how teams choose to do that. So it's not as important that it looks exactly like this as that it is well made. It's designed to handle the stress, and it will and the wiring is set up so it doesn't move around while it's under boost. There's a lot of vibration at that point, and then so that's one of the things that you're going to be looking for is what their avionics bay looks like, how they've got it connected up, are the wires all attached properly, and so forth. And a lot of this guidance is is specifically in the scoring rubrics. So I'm just putting it out right now to sensitize you to that particular issue. Another way to do dual deploy is using what they call the commercial products called the tender descender. And what it is that you only have one parachute, and then you have some type of cable mechanism that keeps the chute partially closed, so that the chute being partially closed essentially acts as a drogue chute. And then when it gets down to 1,500 feet, then that cable is cut or separated and allows that parachute to open fully. And depending on whether you use a commercial tender descender or a cable cutter or some other approach, you've got somewhat different redundancy requirements. That's mainly an issue for the safety reviewers and the high power rocketry judges. But this is a good thing to ask the teams about. Ask them to explain if they're using this kind of reefed parachute approach. Ask the teams to explain to you about this, and make sure that they understand what they're doing and that you understand also what they're doing. Okay. The other thing is different is that all these rockets have to have GPS, and that GPS has telemetry to the Mission Control Center, and those are mandatory. One thing that we found in the 2018 Cup, we did not require GPS, and the teams that had GPS, usually they only spent about half an hour to 45 minutes recovering their teams. But the teams that did not have GPS would sometimes spend 4, 5, 6, 8 hours, sometimes over into the next day out there looking for their rocket. And so we've decided to make that mandatory. Really increases the recovery time, get the teams on and off the range as quickly as possible. We know where the rockets are, and then when the teams go out to recover, the Da Vinci folks in the Mission Control Center will track both the rockets and the recovery teams will have a backpack with their supplies and radios and a GPS tracker, so that we can keep track of both the teams and the rockets while they're out on the range. Some teams will have their own telemetry beaming back data. One of the issues that you have is that some kinds of airframe materials, and even where you put the electronics, can limit the can block out those radio signals. And what particular offender is carbon fiber airframes, because carbon fiber it basically blocks out those radio frequency signals. And so if a team does have carbon fiber, then they're also required to have an RF window, essentially a window of some kind of different material, such as fiberglass, around where its transmitters are, so that that signal can get through. So if you see a team with a carbon fiber airframe, then again you can ask them about their about the radio frequency window that they're and how they're implementing that, because there's a lot of different approaches to do so. And this is one thing that you're going to find is that because this is an engineering situation, there is no school solution. There's no single way to do many of the things here, and so you're going to see several different approaches. None of them are wrong, but some just tend to work better than others, and so teams should be able to explain not only what they're doing, but why they chose to do that in a certain way, because team knowledge is going to be part of how you evaluate how good that team is. If that team is just coming out here and they're bought a bunch of parts commercially and they're just slap it together with an appropriate motor, then that's a very, very basic rocket, and they should get a very, very basic score. Okay. The other thing that we're going to see is student research and developed electronics and avionics, and we're also going to see SRAD motors, SRAD airframes, all sorts of different things. Teams are very much encouraged to use SRAD where it makes sense and where they're able to. For electronics, if the team rolls their own altimeter, it's got to have a commercial off-the-shelf, or what we call COTS, backup. And then either the main the student altimeter or the COTS altimeter can be the primary. It's up to the teams how they want to do that. But the COTS altimeter is the official record for scoring purpose. Now, if they're doing their own avionics, they have to be tested. They have to be tested both for pressure, that the altimeter recognizes the right altitude, and fires the charges at the appropriate point, and that the function has to also be tested. So they can't just put something on a breadboard, come out and fly with it unless they've actually tested. For 30,000 feet competition class, those rockets are going to end up going, through the transonic into the supersonic range, and so they have to, part of their testing has to be, either flight testing or some other way to simulate the transonic to supersonic environment. And the choices of how they choose to do their altimeters are also key. And so again, this is something when you're judging a 30,000 foot team, you really want to try to get them to explain in depth to you exactly why they designed the altimeters, their avionics the way they did, and how they tested them. And so this is something to really pay attention to. Another thing that we're going to see is active trajectory control, because the big part of the scoring, half of the scoring is how close you get to the target altitude. Then one of the approaches that student teams use, not universally, but more and more every year, is an active trajectory thing. Basically, it compares, as the slide says, it compares the current the existing trajectory to some kind of an ideal planned trajectory, and and when the system determines that it's off its proper trajectory, then in the case of a system using air brakes, if it's overshooting, then it's going to deploy some air brakes briefly to slow that aircraft down, to slow that rocket down, and to get it back to where it's supposed to be. There are other methods to use. Gas thrusters, or we're starting to see some of those. Again, those are basically to shape the trajectory by pushing the rocket straight sideways to get it where it needs to be. And so we haven't seen very many gas thrusters, but for the teams that do, again, this is something that you need to get in depth with the teams to make sure that you understand and that they understand what's going on. Now, one of the deals is very important is that active trajectory control system has to lock into neutral if power is interrupted or anything else. And it cannot be active during the boost phase. In the boost phase, things are happening very, very quickly. We absolutely do not want teams to be trying to move that rocket around during the boost phase, because the results would be could be catastrophic. You could have steer that rocket into the spectators area or something else, and the rocket has to be stable without that active control. So if that control fails, that rocket's got to be able to fly on its own in a safe way. And so again, this is something that you need to pay attention to with the teams that are using active trajectory control, how they're safing it, and then how they've decided to implement that. The other issue that we're going to see is transonic and supersonic flights. So there's several issues. One is the fin flutter, is a thing called fin flutter, which I'll talk about in some more detail, and just the stresses that it puts on the airframe. And so fin failure is the primary. The structure of the rocket's gonna break. That fin is the primary place where it's going to break. So this is something that's going to be very important. If you're going supersonic, then the rocket stability is actually going to change there. It's particularly true for the 30,000-foot rockets. And this is something that the teams need to have analyzed thoroughly so they understand what's happening to the rocket stability. If you get going really fast up and over Mach 2, usually not an issue, but you can get heating issues. I've had rockets come back with blistered paint on them, but so this is can have a potential issue, and so a good computational fluid dynamic analysis should be one of the things that they do to rule out heating as a problem. So again, this is something that you want to pay attention to as you judge the teams. So here is a snapshot of a video. It's a little bit exaggerated because of the frame rate of the camera, but you can see that those fins can move around considerably especially at the max Q, that point of the where the motor burns out, where you've got the maximum aerodynamic pressure on that rocket, and that those fins will actually bend, and you can hear it. They go, kind of a burr sound as it's going up when you're doing that. Really is dependent on the fin shape and the material stiffness. Again, this can definitely rip that fin off the rocket, and so the team should pay attention to flutter analysis, looking at their rocket, making sure that they're Generally, we want them to be well below their fin flutter velocity, and they should have figured that out and figured out how they're going to deal with that. So we talked about stability changes. Stability. We talk about in the Rocketry 101. We talked about static stability. That you want to have the center of pressure about 1.5 to 5 or so calibers. Caliber meaning the diameter of the airframe back from the center of gravity. So just like an arrow, the fins are back behind the feathers of that arrow or behind the center of gravity of the arrow, and so that arrow is going to fly straight. Obviously, if you reverse that and through the arrow fin first, feathers first, then it's just going to go somewhere else. But stability changes during flight, and especially as you go through the transonic and the supersonic range, because once the airflow goes supersonic, then you start to get shock waves coming off, which are these kind of diagonal blue lines here, and those shock waves, once those form, they will actually change the velocity of airflow that control surface sees from supersonic to subsonic. So about Mach 0.8, I'm sorry, Mach 0.8, you start getting into the transonic range. You start seeing the shock waves form as the airflow is moving around that surface and becomes supersonic. And then as the faster the rocket goes, then that shock wave is going to move aft, and that's going to increase drag, and it's also going to change the center of pressure. And so then once you get up to like here in the middle signal graphic Mach 1.1, this is still typically in the transonic range because part of the airflow on or near that surface is still subsonic. So you'll often have like a bow wave of subsonic airflow and a little bit of subsonic airflow on the tail. But then once you go supersonic, then that center of pressure is going to gradually, again, change position, usually moving forward. And that's also going to decrease the drag. And it's something, when I was in pilot training many, many years ago, flying the T-38, which is a supersonic trainer, that once you got that jet going fully supersonic, it really smoothed out. I mean, it almost felt like you were welded to a plate of glass. How smoothly the airplane flew in that regime. But getting to that is, you've got stability changes moving back and forth. You've got drag changes, and which is one of the reasons they called it the sound barrier, because you have all these different things going on within the transonic range, which made traditional ways of aircraft control that they had back in the 1940s, didn't work right. But now we understand what's going on, and so this is not as big of a deal as it used to. But you will see here that, for example, here's just a, a typical kind of example where the, your center of pressure is at a certain point. So in this case, it's measured in inches going back from the nose. So here, the center of pressure is starts out about 87 inches, and then once it gets in the transonic range and those shock waves start to form, then that center of pressure is going to tend to move aft, and then once it gets fully into the supersonic range, then that center of pressure will gradually move back forward. Now, this is one typical, because both the nose cone shape and the fin shape are going to affect this, as well as their exact airframe design. And so different combinations, could cause this thing to work differently. And sometimes it's not uncommon for this to work in exactly the opposite direction. Not, generally it works like it's on the slide here, but we can see it. We see some combinations where it goes the other way. And so again, this is something that the student teams should, who are going supersonic or into the transonic range, should have analyzed and should be able to, uh, show you, their analysis, how that how their velocity affects their center of pressure and and therefore their stability. The other thing that we have in here is that these rockets have a tremendous amount of vibration, and so the teams often really underestimate just how noisy, in terms of vibration, those rockets really are. I had a team in 2018 that I helped do the recovery, and when they opened up the rocket to so that we could read their altimeters, their altimeter, their avionics bay simply fell off in little pieces. They had 3D printed the thing. They were not paying enough attention to to the infill and to the printing orientation, and so because of that vibration, that their lovingly designed and printed avionics bay basically disintegrated, and today, even today, it's a mystery to me how that rocket actually worked when that avionics bay disintegrated. The other thing, of course, that vibration will cause is anybody who's driven a car or anything for long distances. The vibration will tend to cause the fasteners to start to unfasten. And so, if you have screw fasteners or nuts and bolts, then they have to use something like Loctite or nylon fasteners or something else to make sure that the vibration loads do not back that fastener off. Wiring, another important thing, the wiring should be snug and neat, but you don't want it tight. It's got to have some strain relief, but all those wires need to be tied down and they need to be firmly attached on both ends so that those wirings that wiring will not work loose under the vibration. And so going from the electronic wiring to electromagnetic interference, I bet you're wondering how it's going to make this transition. Then you have an issue where if you have a GPS transmitter or you've got your telemetry transmitter, and depending on where it is in relationship to the other electronics, that those other electronics can actually tend to block that signal or interfere with that signal, and so they need to make sure that those things are placed in such a way that you're not trying to, transmit your telemetry through the other electronics on the rocket. And the other, of course, electromagnetic interference, which is kind of a mild way to put it, is that these things do have significant uh, some of them do have significant juice. We have one team who's got a payload that's got a kind of an ion thruster on it, and that's carrying a lot of voltage. And so this is something that, as we talked about in Rocketry 101, when the team's going to recover a rocket, they you have the chance of you have hot live electronics. You may have unfired charges, and so this is something that the teams need to be aware of, and that you need to be able to press the teams about. Teams are, as you'll see in their project technical report, they're required to have checklists for their assembly, their launch, the recovery, and they have to have both kind of the normal procedures and they have to have emergency procedures. And so they should be able to tell you if they go to come up on the rocket, how they're going to approach that rocket, how they're going to make sure that that rocket is actually safe, how they're going to deal if it's got unfired charges and so forth. So again, yet another thing and this is part of their scoring, but another thing for you to talk to the teams about and make sure that they're understanding what they're going on. Okay, For the 30,000 foot shots, we got, this creates its own set of problems as well. As I mentioned earlier, most rockets use black powder as a mechanism to separate the pieces of the rocket to put the parachutes out. But at high altitude, the air density is so low that not only is it reduces the heat transfer and lets those black powder grains scatter without burning. And so if you don't contain it somehow so that it burns well, then that black powder is not going to work, or is going to work at much less efficiency than it would at ground level. And so one approach, and there are others, is to basically put your black powder charges into a piece of surgical tubing to make sure that all that black powder is contained at a given pressure. But many teams will actually use carbon dioxide canisters, just like you would find on an air gun, to and use that to generate the pressure necessary to separate the rocket to put the parachute out, and that largely solves the issues of black powder ignition. And so for the 30,000 foot teams, again, this is something to pay attention to. Ask them how they're dealing with this, and make them walk you through it. Okay, liquid motor. We don't have any liquid motors. They're hard to do. This is the Colorado State shot that blew up shortly after clearing the rail, but we don't have any teams this year. Okay, payload. This is another big difference. These rockets for the Cup, they have to carry an 8.8 pound payload. They can either do that as some type of scientific experiment for which they get extra credit, or they can simply have a CubeSat form, boilerplate, payload, with just metal shell with weight put into it, so that it adds up to 8.8 pounds. And for teams that have a scientific payload, if they put that into a CubeSat form factor, then there's a bonus that the Space Dynamics labs folks who judge the payloads will award. Okay. So design quality. Even though we're scoring everybody on the same level playing field, effectively there's really two competitions: the 10K and the 30K. Those two altitude regimes have dramatically different design challenges. 10K, generally you got a rocket that's totally subsonic. It could be a very basic rocket. 30K, you're only going to do well if you're able to make sure it has good performance in the supersonic range. Otherwise, it's not going to get to where they think they're going. So let's talk about 10K. So for your sight picture here, 10K is a basic Cup rocket. We've gotten beyond the point where teams are simply buying a kit and putting it together like we had back in 2017. But it's pretty similar to your standard level 3 AAA or NAR certification launch. These things are subsonic. You can do things. You can do a lot of different things, and they all pretty much work. And so when you're looking at the difference in between 10K teams, one of the things is basically the build quality. How well they do, and how is the fit and finish, how firmly are the fins attached, what have they done. And you'll see some rockets that are very very sophisticated in the way they were built, and you'll see some rockets where literally the people are just cutting their airframes with a hacksaw. One key difference that we're going to see between the two, between rockets is to 10K level, is their efficiency. It's fairly obvious that there's a couple different ways to do this, right? You can have a great big rocket, that's overbuilt, just put a big honking motor on it, and to get you up to 10,000 feet, or you can pay more attention with the smaller rocket, more optimized and get to the same altitude using a much smaller motor. And so you'll see a huge range in terms of overall thrust between 10K teams. Some teams will be in the L motor, and lower M motors, but you'll see some teams who are doing N's and even a few O's all the way up into that. So this is something that will show you big differences, and subsonic drag for the rocket is really affected by the wetted area. In other words, the amount of that rocket that sees airflow creates friction drag, uh, and so that will really change that. And so you'll see differences between the teams that are really trying to optimize on that versus the ones who are going, okay, we got a motor, we got an airframe, this thing gets up to approximately 10,000 feet, we're good to go. And so, those first teams, who really, try to optimize their rocket, try to make it very efficient, those are the ones that you want to be rewarding in terms of your in terms of your judging scores on both design and build quality. When you go into the 30,000 feet shots, you got a different sight picture. This is, now you really got to know what you're doing. You got you're going supersonic with all those problems that we talk about. One of the, things, the shaping of the nose cone, the shaping of the fins, how they're attached, those are minimizing the supersonic drag is really key to how well those rockets perform. And it's a different challenge than you see at the 10K level. And so and beware of simple analysis. So you'll see a lot of teams, they go, oh yeah, we're going to go with the von Karman nose cone. Okay, that's not necessarily a bad answer, but it may not be the best answer. And so, some teams will approach this in a very simplistic fashion, and you should be able to look. Most everybody here is experienced either as a rocketry or in some type of engineering background, and you should be able to tell the difference between solid analysis and the analysis where they just kind of did a lot of hand waving. And the one thing we should be seeing is that teams should do good computational fluid dynamics analysis, because for these 30K rockets, you've got nonlinear turbulent flow across there that teams have to deal with. And so this is one big difference. Okay, so let's shift gears here and talk about the scoring. And so um, this is one area that we've continued to evolve. Um, we're getting more and more to try to make sure that teams have made the appropriate choices for the appropriate reasons. In other words, we don't want teams just slapping together, piece parts that they bought online, and if it gets up close to 10,000 feet, that's it. We're good to go. You're looking for teams who, this is an engineering competition, are doing good engineering for every single part of their rocket. So everything should be done by choice, and choice backed up by analysis and understanding the appropriate trade-offs. So, okay, so that philosophy piece done. Let's look at the nuts and bolts. So 1,000 points, 500 points are due to the flight performance, how close to the target altitude. And usually in previous cups, that difference has usually been under 25 feet. So these teams are, the good teams are pretty good at being able to hit their target altitudes. And then the part that you as judges are going to be responsible for are the 200 points for the project technical report and the 240 points for design implementation, which is broken up into design quality and build quality. And then there's another 60 points that are given by admin things, which actually I've already assigned. So you'll be happy to know that after all the admin stuff, there's a 119-way tie for first place. So the key documents that you're going to see uh, and that are you're going to have to be fairly familiar with design, test, and evaluation guide. That's the student's Bible for how they're going to build their rockets. They set the requirements, the minimum requirements for safe operation, and those requirements have to be met. Um, safety reviewers should have caught any unsafe things before you get to them. But the but still, those are things to pay attention to. And sections 5 to 10 of the DTAG are things that you should be at least familiar with. But the big deal for you as judges are the rules and requirements document, or the R&R. That's got all the rules, it's got the deliverables, and that's got the scoring. And so these sections in Chapter 2 both define the deliverable requirements and the scoring and awards. And especially for you, Appendix B has all the detailed scoring rubrics. Which is how you're going to assign points. The current versions, I have sent you all the latest version. I do not anticipate changing it, but the current versions are always going to be at the Ezra website, soundingrocket.org, and then you look at the drop down for documents and forms, and those are all right there. Or you can just drop me a note. The other place that the current versions are posted is in the 2023 judging channel of our Slack site. And again, if let me put another plug, if you have not joined the Slack site, you need to do that. Okay. So let's think about the items. So the technical report, 200 points. And so the first 60 is basically administrivia. Are all the parts that we asked for there? Did they cover all the bases? Do they have all the required dependencies? Is it well written and in the proper format? Again, that's another 40 points. The majority of this is, what's the analysis like? Is it complete? Is it rigorous? That's the part, that's going to be the bread and butter for your judging task for the technical report. And we're going to talk more about that. The other piece is the design implementation. How well is the darn thing built? Okay, so that's half of that. And does the team, again, in keeping with our emphasis that this is an engineering competition, does that team have a consistent and achievable design vision? Does everybody understand that? You'll see teams where if you ask somebody a question about why they did something, they'll turn around and look at someone else to answer. So you'll see some teams maybe have only one or two real experts, and everybody else is just kind of along for the ride and to help carry heavy objects. If they did student research and development items, were they made with a purpose, or were they just because we can do some SRAD fins or something like that? But there should be a reason for every single thing that's done on those rockets. Okay, so the scoring rubrics basically go in 4 categories: outstanding to unsatisfactory. And this is pretty standard stuff. An outstanding thing is exemplary. You look at that and you go, okay, I got no questions. Then most teams you're going to see are going to be excellent to satisfactory. Analysis is going to be adequate to very good. They're just about most things are the big pieces are covered, but they might have missed some stuff. And then you may see a few teams that are unsatisfactory in some areas, and where they've got major deficiencies. They haven't really thought through their process all that well. Hopefully, the safety reviews will have caught all that stuff before it gets to you. But if you do see something like that you think is really, really questionable, get with me or get with Ken Biba who's in charge of the HPR judges. Folks, and the safety folks are going to have different, have a different colored badges, and get them to give you a read on it, because we don't want, while we don't want the safety people worrying about scoring, and we don't want, we don't necessarily, and we want you to as judges to concentrate on scoring, but safety is really everybody's job. And I'm an old flight safety guy from the Air Force, and did flight and nuclear safety. So, tolerance for mistakes and those things are very low. So if you see something that doesn't look right to you, or that looks potentially unsafe, then you bring it up to one of the safety experts, and we'll get it sorted out. So calibrating your mind. So if you were grading this, in a college or high school, outstanding, that's your A to A plus, excellent or B or better, satisfactory, C minus to B minus, and then unsat is a D or an F. So most teams are going to fall in that kind of middle range, high satisfactory into the excellent realm. But you will see some outstanding teams, some extremely good teams out there. So don't hesitate to give an outstanding if the team deserves that. But you got to be critical about this, okay? And so the rubrics are designed to help you to do that. So let's talk about the technical report. So we've broken up a lot of these into sub areas. Now, each of the judge teams, you're going to have, 8 or 9 teams to score technical reports. That's a lot of technical reports. Even though we've limited the main pages to to 25 for commercial off-the-shelf teams, solids teams, or 50 pages for liquids and hybrids. But they've got a lot of room to put graphics and of course there's required dependencies. So some of those things can be quite long. But your main goal when you're judging those reports is to look at the main part, that 25 pages of main text. That's going to be your focus. You're welcome to look at to review the appendices, but really all we're asking you to do for the appendices is to make sure that they're there. So completeness, it's 20 points. It's pass fail. Everything that's required out of the rules and requirements for the technical report has to be there. And for the in the scoring rubrics, I actually made up a Excel-based scoring rubric for the project technical report, which is on the shared directory, and that actually lists out right next to that category what those required items are, but otherwise they are in the rules and requirements. And then the same for style and format. How well is it written? Is it written well? Are the mechanics good? And did it follow the right format and stay within the page limits? So that part's pretty easy. So here's the style, just as an example. So the outstanding 18 to 20 out of 20. The writing is exceptionally clear. And I'm not going to read you these things, but you can see that as you move to the right, you start to see whether or not you've got, they're doing, they got irrelevant or erroneous information in there. There is a, writing, is the writing going to be clear and understandable? Always, is it just crystal clear, or you kind of scratching your heads over some sentence? So this is how you're going to break out the categories for style. Now, so the analysis part is this is the heart of your task for the technical report, and so you've got broken up as shown. The depth of analysis is the biggest piece. The team's assumptions and sensitivity analysis is another big piece, and whether they did the verification and validation test appropriately. those in charts and figures. Are they, do they add value? Are they just in there for eye candy, or are they unclear and misleading? So those are the kind of things that we're asking you to look at. And so, for example, we're looking at the depth of analysis. For an outstanding report, basically every single design decision has to be discussed. It's got to be based on their targets, the constraints. They walk through the appropriate trade-offs and so forth. And so you'll see, most teams again are going to be in the excellent thing where they're pretty much talking about all the big pieces and just didn't have time or just weren't able to thoroughly analyze everything. But the depth of analysis, this is really what we're getting at in this engineering competition. Did they really do that? And I'm not going to go through again. I'm not going to go through all four of the areas in detail. You've got the rubrics available, and you can certainly raise questions in the Slack channel or just email me if if you don't understand what we're getting at here. Okay, design implementation. What does a well-built rocket look like? So, when you look at it, you start from the tail. You want to make sure that motor is in there, good and solid, that and the fins are solidly attached. You don't want either one of those things to go anywhere because if the motor, shreds through the rocket or if the fins leave, then, who knows where the pieces are going to go. The launch slugs that they use to hang the rocket onto the launch rail, they should be aligned and they should be strong. Those little plastic launch slugs are going to carry the entire weight of the rocket when it's sitting on the rail. And so, you want to make sure those things are, nice and strong, and have the teams pick it up by the launch slugs just to make sure. When they show you how they got their parachutes and shock cords, those things should be nice and clean. They shouldn't have burn marks and scorch marks on them. They shouldn't have frayed pieces. Those things should not be damaged. There's a lot of different ways to fold parachutes. There's a lot of different ways to fold shock cords. Just have the teams explain, why they did what they did, and make sure and so you'll have a good idea of whether or not they're really doing the job right. That shock cord attachment, that thing can see 50 G's of pressure when those airframes pieces separate to put out the parachutes. So make sure those fasteners are tight, and we've got special requirements in the DTEG for the kinds of eye bolts that the teams can use. They can use quick links to fasten the shock cord to that, or they can use knots. And not many teams are using knots anymore. That's kind of old school, but some knots are stronger than others. And so if you sit there and it looks like a granny knot, then you need to make the team explain why they use that particular knot. Again, we talked about the electronics, well mounted, everything's tight in well, wires are neat, nothing's loose. You should be able to pull on those wires right at the point where they come into the battery or where they come to the attach into their flight computers, and those things should not go anywhere. You should also not see any loose wiring strands or anything like that, because that's definitely a safety issue, and teams have to fix that. And then again, like we talked about with the 10K teams, the overall fit and finish of the rocket. You're going to be able, some rockets are going to be really, really nice looking. Some rockets are going to be kind of raggedy. So that's that's part of the scoring criteria. Okay, so design implementation. The first piece of this is build quality. Design quality, is it robust to the system, to the environment that it's going to see? Have they, are the parts manufactured well? Are the construction methods appropriate? And this is especially in terms of in terms of 3D printing. Again, the infill, how many walls, what the orientation of that thing as you printed it. All those things are important to consider. Uh, is the design consistent? This is a lot of these student teams, they've got one set of folks working on the airframe, one set of folks working on the fins, one set of folks working on the avionics, one set of folks working on the motor, and so forth. And it's not terribly unusual to see those uh, teams working at cross purposes. The classic issue here is that you've got the aerodynamic folks who are trying to make this rocket just as slick as possible to decrease the drag, but the rocket is already overshooting its target altitude, and so what? You're going to make it overshoot even farther by doing so, by minimizing drag. So the team should all be working to the same goal and should all be understanding how those pieces affect each other. And then again, compliance with the DTAG. If they're not compliant to the DTAG, then the best, if they're anywhere place where they're not compliant with the DTAG, and this is in the rubric, the best they can score on build quality is 60 points. So, this is something that teams have to, absolutely have to do. Okay, so let's talk about design quality and robustness, just as an example. Um, an outstanding rocket, it's going to be more than sufficient to operate under, reasonably expected conditions. That rocket's going to be, very, very solid. It's not necessarily overbuilt, but, you're pretty well are going to, it's going to take anything you can throw at it. Whereas if you get down in the satisfactory range, the rocket's probably well enough designed to handle launching in calm winds or with low winds, but may have trouble if you're launching at higher winds. Again, this is something the safety folks are going to pay attention to, but this is so we're trying to get a handle on is that rocket not only going to work as advertised, but is it going to work as advertised under all the expected conditions that it could see. So this is a important part of that grade. Okay, so then the other part of this is the design quality and decisions. Again, the big piece is the team design vision, the goals, the system engineering. Is this how fully integrated is the team's design based on what they needed to do, what kind of constraints that they might have had, whether that be um, financial or the ability of their local labs to test things, or the kinds of manufacturing capability that they have access to. They need to. Again, everything should be done by choice. Everything should be done backed by analysis. And that good systems integration, as I kind of touched on earlier, this is an area where the you know, teams tend to fall short, where the individual piece parts are all nice and optimized, but the rocket as a whole is not. So the other 50 points is the use of SRAD components. Again, we want the teams to design and build their own components as much as possible where it makes sense. Why did they choose to do this, and what benefit are they going to gain out of it? And then the last piece is team knowledge. Again, if the team is, if you ask anybody on the team about something and everyone can give a pretty coherent answer about it, that team's got pretty good knowledge. Everybody knows what everybody else is doing and can articulate that. But as you'll see when you talk to the teams, a lot of times the teams will defer to a few experts, or even worse, they may defer to their triple E mentor or flyer of record. And if every time you ask a question and everybody looks at the flyer of record to for an answer, that's not good, because then that means that the teams are basically doing something without really understanding why they're doing it. And so team knowledge, an important separator between good teams and bad and not so good teams. Okay, so then let's look at the middle section, the SRAD components. So an outstanding rocket's going to have lots of SRAD components. They're clearly chosen, to achieve various goals, and that could be, a design goal, or it could be a strategic goal. Some teams have got multi-year programs going where they're trying to advance the overall team knowledge and skills over the years to create a successfully higher quality of things. So, if the team decides they want to do an SRAD motor because they think that that's that they're going to need this in the future, and that they're going to build an SRAD motor this year because that's their next step. That's their next logical step. That's an acceptable reason to do that. And again, that if you look down in the satisfactory, the unsatisfactory, then you see that teams, where teams do something just because, or just because the team before us, or last year's team did this, so we're going to do that too. That's not a good reason. That's they need to, again, everything's got to be by choice. It's got to be understanding the constraints, and it's got to be based on their analysis. Okay, the other scoring pieces that we haven't talked about too much is the podium sessions and the technical awards. Now, teams, we're going to have 24 teams chosen based on their extended abstract and slide deck, and those things were both submitted along with their project technical report. And by being chosen for those podium sessions, and they are in the running to compete for the 3 technical awards for technical excellence, for innovation, and for modeling and simulation. And we're going to defer teams to teams who successfully launch. So a team can have a pretty darn good podium session, but if they don't get their rocket off the ground, then that's going to knock them down in consideration for the technical awards, versus a team that also had a good podium session, but were able to successfully launch. There is a 4th technical award, the Barrowman Award for simulation, or for flight dynamics, and that's based on how close the rocket actually came to where it predicted it would come. And those the teams that scored very well on that were extremely close. The winning team last year was in 0.14% of their planned altitude. So that's pretty darn good. We're talking about a difference of 14 feet between what they're simulated and where the rocket actually went. So those are those things. So one of the things I'm gonna ask you to do, and I'm gonna send out an email kind of reiterating this, is to look at the team's extended abstract and slide deck, and if you think that they've got some good ideas that makes them competitive for one of these 3 awards, then you need to nominate those teams for podium sessions. And when you do that, then you're also going to be able to, along with other judges, sit in on those podium sessions and grade those. So podium sessions, because it's dependent on part of the criteria is dependent on whether they actually fly, then we're going to have a very, very simple rubric just to focus the discussion, to make sure. So basically, 3 points which are aligned with the with the 3 technical awards. So in terms of 0 to 30 for technical excellence, 0 to 30 for innovation, and 0 to 30 for modeling and simulation, and then 10 points for presentation quality. How well did they do the thing? But the emphasis is obviously on the substance and not necessarily on the presentation quality. Um, but usually, if they get the substance right, usually the presentation is going to end up being high quality. But this will allow us to focus the discussion to figure out which teams are competitive for which awards, and then once we get the flights in, then we'll be able to cut the discussion down to just a few finalists for each one, and move on from there. Okay, so other things, they have there's bonuses and penalties. So if the teams are being unsafe or they're acting unsportsmanlike, uh, then that's a 20-point deduction, and you can, if you see that happening, write it down. Let me know. Let Ken Biba know, and we'll keep track of that. We usually do not see this, but for example, in one competition, um, one of the requirements when launches are going on, that the teams and everybody has to be, out from underneath the tents, because we don't want somebody under the tent when rockets flying. We want everyone out in the open where they can watch the rockets and make sure that they're not going in the wrong direction. And so, for example, we had one team who just refused to come out. They just wouldn't do it, And so we started hitting them with unsafe conduct penalties, and that kind of changed their mind. So that's it's those kinds of things. Or if you see teams who are got their pyrotechnics out, their black powder charges, or they've got their rockets pointed in an unsafe direction while they've got the motor in, or anything like that you think is unsafe, or that they're just being bad competitors, they're being nasty to their fellow Rocketeers, or they're trying to undercut them, or things like that, then that's a 20 point ding, and repeat is necessary. I talked about it already. There's a CubeSat payload bonus, which the Space Dynamics Lab folks will give us, and then they have a bonus for efficient launch preparation. We had to put this in after the 2017 Cup because it became apparent real quick that the teams were not all that anxious to get out in the desert and get their rockets launched. A lot of them were just staying in town until literally the last day of the Cup, and then coming out and trying to launch, and it did not go well for them. And so, being students, if you give them bonus points, then they react to that. And so, if a team is launch ready on Wednesday and they fly on Wednesday or Thursday, then that's 100 points, and then so forth for flying on Thursday and Friday. So we want the teams to lean forward and get launched. We've got a lot of rockets to launch this year, so we need to keep up a pretty good pace. And the way you keep up a good pace is getting those teams out there and ready to go. The other thing that we will issue you is you're going to have basically a handful of poker chips that when you see a team that's really, or a team or a person who's really doing something, doing something good, showing good sportsmanship, really paying attention to safety, then you can give that poker chip on the spot for team members that are doing that, and those are actually fairly coveted items, and so that's just a good way for you to say, wow, you really impressed me by what you did. Here's an award for me for doing that. So this is something that you've got the flexibility to give out as you want. Um, we don't want you to hoard your poker chips, but if you don't see anything that warrants it, then then that's up to you. All right. And so other teams, there's 2 other awards: the Team Sportsmanship Award and the Team Spirit Award. Those are pretty much explanatory. Um, you know, in one year, we had a team from a little tiny uh, liberal arts college out on the East Coast. Three guys who their school gave them a grand total of $500 of support, and you will see that some of these teams get thousands and thousands of dollars from their schools and from their sponsors. These guys, put this thing together on a shoestring. They schlepped their rocket clear across the country on the back of a Volkswagen Beetle, and they launched. But the thing that really made that special was that you had another team from Egypt, who was there was their military technical college, so they got full support of the government. The government put them on a C-130 to fly them over here with their rocket. They had two rockets they were going to launch, but they were going to reuse the components from one rocket to launch their second rocket. And as fate would have it, their first rocket just blew up on the pad, and so no chance for them to get their second rocket off. But it was that team from that little liberal arts college who gave the Egyptian team, well financed and supported by the government. They gave that team what they needed to be able to fly, and so that's the classic to me picture of what good sportsmanship's all about. And then the same thing, the Team Spirit Award. You know, some teams are just upbeat. They're just really representing their school, representing their country, as the case might be. And so this is again an award that really means a lot to the teams. Okay, so nuts and bolts on how we're organizing things. So we've got two different kinds of judges, as I talked about in my earlier emails. You got your high-powered rocketry judges and your technical judges. High-powered rocketry judges are experienced folks who are level 2 or level 3 certified, and they are responsible for scoring the build quality. And so they're going to be in a central location at the vertical launch area, kind of one-stop shopping for the teams to be able to come to them, get their rockets inspected, get their rockets judged for build quality. And so they're largely in charge of that, but they're also your technical support for the other judges. So if you're a technical judge and you're looking at this rocket and you don't really understand what that team is doing or whether that's a good thing or not, then go over to the tent where the high power rocketry judges are and say, hey, I need your read on this. And they're going to be, so they're a resource for you as well. So that most of you are technical judges, experienced folks with background in aerospace or engineering or some kind of space launch. And so you're in teams of three covering 8 to 9 schools, and you score the technical report and the design quality. And then both the HPR and the technical judges are going to score the podium sessions. So that's kind of the division of labor. Now, for your technical judges, like I said, you're going to have up to 9 schools to 9 technical reports to score. That's a lot of technical reports. So accordingly, I've given you the opportunity to divide the labor a little bit, so that you can have, so you can divvy up those schools in such a way that each school gets 2 scores. So the three of you got um, 9 schools to technical reports to judge, and so you can say, okay, one of us is going to take 6 schools. Another one's going to take 6 schools. The third one's going to take 6 schools, and as long as each technical report gets 2 scores, I'm a happy camper. And so it's up to the team how you wanted to divvy up the labor, or even if you do, if everyone wants to score all the reports, hey, that's great. I'm just giving you the opportunity to lighten your load a little bit. Some of us have real world constraints, and I'm sensitive to that. I don't want to overwork you too much. We're going to be working hard enough as it is once we get out to the competition, and so that's the divisional that's the potential divisional labor. So okay, so the judging flow. Here's, so we're in the prior to the cup stage, review and score technical reports. That is going to be your main task. Okay. Those need to be done before the cup starts. So by the 18th of June, so, not quite a month from now, you need, all the technical reports need to have been scored. And also before the cup, uh, I need your recommendations for teams for podium sessions. Usually we usually have about the same amount of recommendations as we have for slots for podium sessions, so it usually works out pretty good. But we may have to, down select, or we may have to shake the trees to try to get some more. Okay. Then once the cup starts on the 19th, that's the day that teams are checking in to the Las Cruces Convention Center. That evening, we will have the judges kickoff meeting, and it's our first event together. It's going to be, probably 6 o'clock. It's either going to be at the convention center or at one of the nearby hotels. We haven't quite determined that, but I will, let everyone know well in advance. But that's so if you're working on travel plans, uh, as long as you can make it to the judges kickoff meeting, we're good to go. So then Tuesday, then teams are going to be doing their poster sessions. So they're going to have their display set up, the rockets there, the teams there. And so this is going to be your chance to walk around the convention center and start assessing the team's design quality and build quality. And if you're efficient, you can get a lot of your judging done in air conditioned comfort, which is definitely a plus. If one of your assigned teams is given a podium session, then you need to sit in on that podium session and start and assess the teams for technical excellence awards. You can also use their technical report, kind of just to, help you understand what they're doing. But your main focus for your assessment is on their actual presentation, not necessarily the things that are in the technical report that they didn't talk about in their presentation. So Wednesday, the teams are going to be traveling out to the spaceport vertical launch area to start setting up, and we should be able to start launching teams on Wednesday afternoon. So one of the things you need to make sure you check with your teams, if they are really serious about trying to launch on Wednesday, then those teams need to get judged first to make sure that you've scored them for the design and build quality before they launch. Because once they launch, you can't score them. So that's got to happen. And Saturday evening or Saturday afternoon, the launches stop at noon, and then we will convene at the Strategic Operations Center at Spaceport America for our final judging deliberations. Not everybody has to come to this. Okay, just because of the size of our judging pool, I would like teams to basically have one representative for each team attending the final judging deliberations. And so those of you who have who need to get out on the earlier side, this is a good chance to let one of your teammates handle the final judging deliberations, and then you can head out early if you need to. And you know most judges like to be out there for the entire competition, even if they finish their judging. They like to be out there to watch to keep interacting with the teams, to watch the launches. That's up to you. I'm a firm believer is that if you don't have anything to do, then you don't need to do it out in the desert. Unless that's what you want to do. So, that's all up to you. Saturday evening is the award ceremony back in Las Cruces. Again, most judges like to go, but that is entirely optional for you. You already know you all will already know the results before that, but that's the last item. And so again, if you've got constraints in terms of your travel or something like that, that's entirely optional. You don't have to do that. Okay, judging aids. Okay, we've talked about the scoring rubrics, the Appendix B of the rules and requirements. You have to use the scoring rubrics, and we will provide hard copies of those at the judges' kickoff meeting, so that you can for the build quality and design quality, so that you can use those. As I mentioned, I've got there's both just a regular print copy version of the technical report rubric, along with an Excel version if you want to use that. And then I also have created a note-taking aid that some judges like to use. All those things are available on the shared drive, but we will provide hard copies of the scoring rubrics and the note-taking aids at the judges' kickoff meeting, so you don't feel like you have to print them out. We'll have plenty of copies to go around for everyone, and that's that, and that'll be all available. Okay, so that is all I have for this. And again, I'm sorry that my bandwidth constraints are making it so I can't do this live. But if you have questions, then the place to ask the questions is in the Slack channel. And again, I will put out a message with the links to the Slack channel and to the links to the shared drive, so that you can download rubrics or download any of the documents that you see fit. The version of this presentation will be there, as will the slides. So you have ample opportunity to go back and review this. This presentation will also be posted on YouTube, which is why I didn't put the links to the shared directory and so forth on it. But if you got questions, if you got concerns, get with me. Something's like, "What the heck are you talking about, Bill?" Then ask that question. Not all of us are experts in the same place, and so this is, if you got a question, chances are someone else has the same question. So don't hesitate to ask that. Primary place to do that will be on the Slack channel, but if you forgot about that or you can't get on it, just send me an email, and I'll address it. Okay, well, thank you very much for your attention. I really appreciate your willingness to judge and to help out, and I am really looking forward to seeing everyone at the cup. Thanks very much.